Now we're going to talk about some properties of polynomials. So first up, polynomials are continuous. We can draw them without lifting our pencil. The domain of all polynomials is always, no matter what, negative infinity to infinity. So when we say that polynomials are continuous, what this means is that there are going to be no breaks or jumps or missing points in our graph. So some things that we won't see in our graph are, so let's see, so no break, so where we have function defined and then a gap and then the rest of the function. We won't see any missing points. This. Jumps. Jumps was next. Okay, so we won't see any jumps where our value changes all at once. And then finally, no missing points. Or anything's left out. Okay, so this is a pretty good definition of continuity. You'll learn more about it if you take a calculus class. Another really important property of polynomials and other functions that are continuous on a negative infinity to infinity is this property called the intermediate value property. What it says is that if the output of p of x changes from positive to negative or from negative to positive, then at some x value, there's some x where our output was exactly 0. So let's draw a little sketch to express this. So here we have the line y equals 0. So this says that if our value if we have a continuous function on an interval and we have a sign change from a to b, then at some point, no matter what is going on with our function, like it could be doing like crazy things, but at some point it has to cross the x-axis. And so there's going to be some point where we have a 0. So what this says is anytime we see a sign change, all sign changes in p of x produce have a zeros in between them. They may have many zeros. So let's also look at another example. So we were positive at B. We're going to look from B to C. C is going to be negative. We may have like many zeros in between them, but it just ensures that there must be at least one. And here we see multiple, but there's definitely going to be one. Another way of saying this is we can't skip zeros. If there's a sign change, there is going to be an x value that produces a y value of 0. Okay. So a consequence of this is that if we write out all zeros of our function, of our polynomial p of x, then once they're all written out, the intervals that lie between them have to contain no sign changes. You can't have any sign changes because any any sign changes would give us more zeros. Okay, so let's take a look at an example of this to help us understand a little bit better. So we had been looking at this example, p of x equals x to the fifth minus 4x cubed. We rewrote this as x cubed times x minus 2 times x plus 2. And we found 3 zeros. The zeros we found were x equals 0, x equals 2, x equals negative 2. Okay, so what are we doing? We're going to build what's called a sign chart. What we're going to do is we first find our zeros. Then we're going to draw them in. In the order they are in the real line, negative 2, 0, and 2, with a dot for every 0. Okay. And we said anytime there's a sign change, there has to be a 0 in between them. So there cannot be any sign changes from 2 to infinity, because that would give us another 0. There can't be any sign changes from 0 to 2, from negative 2 to 0, or from negative infinity to negative 2. So just one sign in each of these 4 intervals. Okay. So once we have our zeros listed, we can find the sign and find if p of x is positive or negative in an interval just by testing one value. By testing one value. And by testing, what I just mean is that if you take some point, let's say 3, in the interval 2 to infinity, we can calculate what p of 3 is. P of 3 here was 3 to the fifth minus 4 times 3 cubed. Okay. So this is 3 squared times 3 cubed minus 4 times 3 cubed. So 9 minus 4, or 5 times 3 cubed. This is positive. And we're not allowed to have any sign changes. And so what that means is on this throughout this whole interval, we're always going to be positive. So we're positive at every x value that is greater than 2. All right, from 0 to 2, we already have all of our zeros written. There's only one possible sign of the y value. Either the y value is positive throughout 0 to 2, or it's always negative. And so one easy way to figure out which it is to choose some value. It doesn't matter what value. You could use 0.1, you could use 1, you could use 1.999. Any value in 0 to 2 will all have the same output. So let's, in terms of its sign, so if we look at p of 1, it's equal to 1 to the fifth minus 4 times 1 cubed, or 1 minus 4. This is negative. So what that means is throughout 0 to 2, at every single x value, we are going to be negative. So I'm just drawing a big old negative sign to tell us throughout here, we are negative. All right, from negative 2 to 0, we're going to do the same sort of thing. We can choose a value, let's say negative 1. P of negative 1 is equal to negative 1 to the fifth minus 4 times negative 1 cubed. So this is -1 minus 4 times -1. So that's -1 plus 4. This is positive. I'm going to draw that in with a yellow for all of the x values where the output is positive. All right, take a moment, try out this last interval, and evaluate at your favorite point. So we get -3 to the 5th minus 4 times -3 cubed. So this is 9 times -3 to the 5th, 3 cubed, minus 4 times -3 cubed. This is going to be 5 times -3 cubed, which is negative. Okay, one thing we kind of noticed here is that we have, as we're writing out these terms, sometimes we have to like pull out our calculator to, we may want to pull out our calculator to look at the signs. If we have things in a format where everything is all factored, there's a somewhat simpler way of finding what the sign is going to be, which is that it doesn't, we don't really care what the output is, just the sign of the pieces. And so if we look, for example, at this input of 3, we have 3 cubed times 3 minus 2 times 3 plus 2. So this is a positive thing times a positive thing times a positive thing. 3 positives multiply to give us a positive. If we look at 1 cubed times 1 minus 2 times 1 plus 2, in this factored form, it's all we need to really worry about is the sign. We have a positive thing times a negative thing times a positive thing, and they're going to multiply. We've got 1 negative, so they multiply it to give us a negative. And we can do the same sort of thing for the other terms. We have -1 cubed times -1 minus 2 times -1 plus 2. This is a negative times a negative times a positive, which gives us a positive. Great. So in general, we're going to see that the behavior of our graphs, we have like, it's not too bad to write out what things are going to look like if the multiplicity of a term of a 0 is even or if it's odd. Okay, so we're looking at the multiplicity of the 0 x equals a. In the case that it's even, there are kind of two pictures of what can happen. We're looking at a. So for example, we might see a term that looks like x minus a squared as a factor in our factorization. X minus a squared is not going to change sign. Okay? If you plug in x values a little bit more than a and a little bit less than a, they both give you positive values here. So our sign chart, when we have an even multiplicity, is going to look like plus on both sides of the a. When this happens, we'll say that we touch the x-axis. Or that we bounce at a. So either we could be positive on both sides, or we could be negative on both sides. In which case, right, it'll look like this. Our sign chart will be negative, negative. So anytime you see an even multiplicity, there won't be any sign change across it. If you have an odd multiplicity when there's a 0 at x equals a, for example, if you have x minus a cubed, well, on one side it'll be positive because we're taking odd powers here. Odd powers remember the signs of their inputs. And so there are two kind of pictures that we might see. Things might look like this, where we're positive on one side and negative on the other as a, or the reverse. We might be positive to the left and negative to the right at a. In the sign charts, let's just draw out what this looks like. At a, we have a sign change. To the right, we were positive. To the left, we were negative. In the second example, at a, to the right, we were negative. To the left, we were positive. And so here, we're going to cross the x-axis. And so just returning to this example where we had p of x equals x cubed times x minus 2 times x plus 2. We have our zeros, got negative 2, 0, and 2. Okay. We can choose a point, let's say 3, to decide the sign. In this case, at 3, we see that this is positive. I was using yellow for positive. We're positive from 2 to infinity. Okay. Here at 2, let's look at that term that corresponds to 2. I'm going to color code this. So at 2, this corresponds to this term, x minus 2. This is an odd multiplicity. So we're going to see a sign change. We go from positive to negative. Odd multiplicity gives us a sign change. Okay, next up, we are here at 0. That corresponds to this term x cubed. X minus 0 quantity cubed. That's, again, an odd multiplicity. So we're going to see a sign change. We're going to go from, we were negative to the right, so we're going to be positive to the left. All right, and then finally we had x plus 2. Okay. That corresponds to this point here, this final 0 at negative 2. Again, x plus 2 has, we've got multiplicity of 1, so there's going to be a sign change. And if we were positive to the right, then we're going to be negative to the left. Okay. And so what this lets us do is fill out our sign chart with kind of minimal calculations. And often people are just a little bit more accurate when they fill things out in this way. All right. Very good work today, folks.